Okay, so we are doing the review, and we're doing the review on Lewis structures. So here we go. The first thing that you have to be able to do is to draw electron dot diagrams. Now, remember with these review videos, do not forget to read through the whole thing, try to do it yourself, and then when you get stuck, come to the video to watch the video for the answer or to check your answers, but don't watch it without trying it on your own first. All right, so if you have chlorine, this is our electron dot diagram for chlorine, and the way that you're supposed to do it is that you're looking for the number of valence electrons that chlorine has. And so if we pull up our best friend and we look at chlorine, let's kind of erase some of this stuff. If we look at chlorine, what we will see is that chlorine is in this group right here, group 7A. So everybody who's in group 7A, we call them the halogens. These have 7 valence electrons. So what do the dots represent? They represent valence electrons. And when we draw them separately first, 1, 2, 3, 4, then we pair them, 5, 6, 7. So now I have 7 valence electrons around chlorine. So now it says draw the electron dot symbols for the main elements in living things: carbon, nitrogen, oxygen, hydrogen. So let's do carbon first. We're right here. So carbon's in group 4A. That tells me I have 4 valence electrons. Nitrogen is in 5A. I have 5 valence electrons. Oxygen is 6A. Oxygen has 6 valence electrons. Now, hydrogen, on the other hand, is way over here in group 1, and so only has 1 valence electron. So if we go ahead and we draw these, carbon has 4. 1, 2, 3, 4, and remember we leave them unpaired. Then nitrogen, 1, 2, 3, 4, and then we have to pair up a third one. Doesn't matter. Pair up another one. So now we have 5. Oxygen has 1, 2, 3, 4, and then we need 2 more, 5 and 6. Doesn't matter. And hydrogen only has 1. So it doesn't really matter what side you put them on, so long as you do them singly and then pair them. All right. How many electrons are shared from each chlorine in figure 1 when the covalent bond forms? So all that's happened here is that each chlorine atom had 1 electron that's not paired. And it's kind of just floating out there. And so this chlorine is saying, hey, would you like to share this one if you share that one with me? And so these 2 electrons are the ones that are between the 2 chlorine atoms. And so these 2 electrons together become 1 bond. So how many electrons are shared from each atom? So each atom shares 1 valence electron when the bond forms. So what does the line between the 2 chlorine atoms represent? So here's the line. That line was these 2 red dots. So the line represents the 2 shared electrons between the chlorine atoms. So they're just the shared electrons, and that's what makes a covalent bond, is that it's a shared pair of electrons. So we call this a shared pair of electrons. And one electron from the pair comes from one chlorine, and 1 electron from the pair comes from the other. So it's kind of important to be able to look at the periodic table and to identify trends that are happening. So let's look at the different elements in this table. So first we have element hydrogen. How many valence electrons are in hydrogen? We already said that. We have 1 valence electron. How many more electrons does hydrogen need to fill its octet? And now I don't like the word octet. I like to say a full outer valence shell of electrons, because then that could be the 2 that hydrogen would be happy with, because it fills that first principal energy level. So it only needs 1 more. Then if we look at the number of bonds formed. So however many electrons are needed, that's exactly how many bonds are going to form. So you see this really cool relationship. And that tells the number of shared pairs of electrons. Now, if you want to know how many total electrons, you take the number of bonds formed times 2. That gives you the number of bonded electrons in the molecule, because one bond is 2 electrons. So all we did was multiply by 2. So now, the next question is, how many lone electrons do we have? So I've kind of split this into 2. And so I've said, okay, in that very first column, this is the number of valence electrons in the lone pairs. And then the next column is number of lone pairs. So if you had none, you have none. All right, now let's keep going to chlorine, and we'll start to see some things. So in chlorine, chlorine is right here. And so it's in that 7A group. And so it has 7 valence electrons. It only needs 1 more valence electron to be happy. So how many bonds is it going to make? 1. How many electrons are in that bond? 2, because 1 times 2 is 2. Now, how many lone pairs of electrons do we have in the molecule? Well, how many are left? If I started with chlorine and I had 7, 1, 2, 3, 4, 5, 6, 7, and I shared my 1 valence electron with some other atom, it doesn't matter. How many lone pairs of electrons do I have left? 1, 2, 3. I have 3 lone pairs. How many electrons are in those 3 lone pairs? To go from here to here, all I did was multiply by 2. So what you should get, if you look at the number of electrons that are bonded and the number of electrons that are in lone pairs, those should equal to 8. So if I look here, 2 plus 6 give me 8. Okay, so the same thing's going to work. Let's do carbon. You should pause. You should try to do it yourself. Carbon is in group 4A, so it has 4 electrons, valence electrons. It needs 4 more to complete its octet. So if it needs 4, it's going to make 4 bonds. 4 times 2 gives me 8 bonded electrons. Well, if I already have 8, can I have any lone pairs? No, I have no lone pairs, so therefore I have none in the lone pairs. But I still have a total of 8 because they're all in the bonded. Okay, nitrogen. Nitrogen has 5 valence electrons, group 5A. It needs 3 more electrons to have a complete outer octet. If it needs 3 more electrons, it's going to make 3 bonds times 2 gives me 6 electrons. I know I need a total of 8. So where are those other 2 electrons? And you can prove it to yourself. Nitrogen, right? 1, 2, 3, 4, 5 electrons. It's going to make 1, 2, 3 bonds. So then how many lone pairs are left? 1. How many electrons are in those lone pairs? 2. 6 plus 2 give me 8. Okay. Oxygen. Oxygen is in group 6A, so it has 6 valence electrons, needs 2 more electrons in order to have that complete octet. 2 more tells me I'm going to make 2 bonds times 2. That gives me 4 bonded electrons in my molecule. Then how many lone pairs do I have? So if I'm oxygen, I had 1, 2, 3, 4, 5, 6. So if I have a bond here and a bond here, how many lone pairs do I have left? 1, 2. And how many electrons are in there? 4. 4 plus 4 gives me 8. So now you kind of see the patterns and how we know how many bonds are going to be made and all that kind of stuff. Okay. So now, this is a really cool table that shows you the different bonding patterns that main group elements can make. And if you kind of think about it, it makes sense. Carbon wants to have 8 valence electrons, but only has 4. So it can make 4 single bonds. It can make 2 singles and a double. It can make 2 doubles, or it can make a single and a triple. Either way that it does it, it'll have a total of 8 valence electrons, so it will be happy. So which ones can make a double bond? Well, carbon can make a double bond, nitrogen can make a double bond, oxygen can make a double bond. In order to make a double bond, you need to have a conformation that requires at least 2 electrons. If you have a 7A group element, they can only make 1 bond, so they can't make a double bond. So carbon, nitrogen, and oxygen. Triple bonds, you would need either nitrogen or carbon, because oxygen only wants to make 2, so carbon and nitrogen. All right, so review the information and write a sentence that describes the relationship between the number of valence electrons and the number of bonds they typically make. So I'm going to make this math statement, and I'm going to say 8 minus the number of valence electrons in an atom give me the number of bonds the atom typically makes. So if my atom is like carbon and it has 4 valence electrons, 8 minus 4 tells me I need to make 4 bonds. Nitrogen is 5 valence electrons. 8 minus 5 tells me I need 3 bonds. Oxygen is 6 valence electrons, so 8 minus 6 gives me 2. I need to make 2 bonds with oxygen. Fluorine has 7 valence electrons, so 8 minus 7 gives me 1 bond. So now I have this really nice way of knowing how many bonds every single atom is going to make. It makes it so easy. So all I have to know is what group something is in, and I can figure out how many bonds it's going to make. So tell me the group and then how many bonds. So carbon is in 4A, fluorine is in 7A, phosphorus is in 5A, oxygen is in 6A. So 4A has 4, wants to make 4. 7A has 7, wants to make 1. Phosphorus has 5, wants to make 3. Oxygen has 6, wants to make 2. So the same thing is true. You could do this with any element. Chlorine is in 7A, silicon's 4A, sulfur 6A, nitrogen is 5A. So no matter what element is in 7A, how many bonds can it make? 1. Anything in 4A is going to make 4 bonds because it needs 4 more to complete its octet. Notice each of these is adding up to 8. That's really important. Okay, 6A and 6A, it's got 6. It needs 2 more to complete its octet. And then 5A and 5A, you need 3. Okay, all right, hope that helps. And let's see. Oh, part 2. We've got to do part 2. We're going to draw more complex structures. Okay, so let's come down. You should have read through all that. How many electrons surround the carbon atom in methane? So if I look at methane, this right here is a single bond. A single bond is 2 valence electrons. Okay, I have a single bond, a single bond, a single bond. So that's 2, 4, 6, 8. So how many surround it? 8. How many electrons surround the nitrogen atom in ammonia? 2, 4, 6, and don't forget my lone pair, make 8. All right, so following the examples, draw the Lewis structure for water. So let's try water. All right. Water is H2O. So my oxygen is going to be in the middle. And then let me do my Lewis dot structure. So I'm going to go 1, 2, 3, 4. And then I got to start pairing up. And I'm going to do, and I just got rid of my periodic table, but how do I know which ones to do? I know oxygen is in group 6A, so it has 6 valence electrons. So I'm going to do 5, 6. Then I have hydrogen. I have 2 hydrogens. They each have 1. So I'm going to turn those individual electrons into shared electrons and share them between the 2 elements, and I'll get 2 single bonds. Technically, the structure really looks more like this. It's bent, but we'll get to that. Okay, so how do I know if this structure is right? I count around each atom and I say, do I have a complete octet? If I first check the oxygen, I'm going to go 2, 4, 6, 8. Okay, oxygen's good. Now hydrogen has got 2, but that's okay because hydrogen's happy with 2. And so this looks like a good structure to me. You can check it with the needed available shared method. In water, we have 2 hydrogens. Let's see if I can kind of zoom in here. We have 2 hydrogens. Each hydrogen needs 2 electrons. Then I have 1 oxygen that needs 8. So that gives me needed 12 electrons available. My hydrogens only have 1. My oxygen has 6, so I only have 8 available. So needed minus available gives me 4 electrons. Divided by 2 tells me how many bonds. I have 2 bonds, and that's how many I put. Now, how many lone pairs is my available, which was 8, minus 4, which was my shared. 8 minus 4 is 4 electrons. Divided by 2, I get 2 lone pairs of electrons. And that's what I did. I assigned them to my oxygen to complete the octet. So it looks good. All right, now we have CH3, CH3. So hydrogen can't be a central atom because it can only make 1 more bond, so you can't put that. So I'm going to put my carbons, and I'm going to go 1, 2, 3, 4, 1, 2, 3, 4, turn that into a bond. Now, I have 3 hydrogens for every 1 carbon. So that tells me that each carbon needs a hydrogen, and each hydrogen has 1 bond. And so what I'm going to do is now I'm going to bond those hydrogens to the carbons by sharing those valence electrons. It's just a single bond. Okay, so now I have, and if you were turning this in, you would redraw that, and you would redraw it like this, just so it was clear to me what you were trying to draw. Okay, so you check each atom. My carbons have 2, 4, 6, 8. Then the next carbon has 2, 4, 6, 8 electrons, and that's great. And then each hydrogen has 2. So it looks good to me. That looks like a good structure. You can check it. You know you have 2 carbons. Each of those carbons needs 8 electrons. Then you have 6 hydrogens. Each hydrogen needs 2 electrons to give you a total of 28. Then available, each hydrogen only has, let's 2 carbons. Each carbon only has 4. Then we have 6 hydrogen, and each hydrogen only has 1 for a total of 14. So 28 minus 14 gives me 14. Divided by 2 gives me 7 bonds. Do I have 7 bonds? It looks kind of crazy with all these circles on here. Okay, so yes, I have 7 bonds there. And then if I want to know how many lone pairs, I do my available, which is 14, minus my shared, which is 14. That's 0, so I have no lone pairs. And that's correct. Okay, draw the Lewis structure for carbon dioxide, CO2. So carbon is our central atom. Give it 1, 2, 3, 4. Oxygen, oxygen has 5. 1, 2, 3, 4. And we'll give it 5. 1, 2, 3, 4, 5. Okay, so what I have to do first is to connect my outer atoms to my inner atom. And that looks pretty good. Like we're making some progress, but nobody's really happy with a complete octet. So what are we going to do? We're going to start moving our electrons. So take 1 from each atom and move it in to where we can make another bond. So now instead of having a single bond, we have a double bond, but not everybody's happy. So let's continue and do the same thing on the other side. We take 1 here, and we take this one here and we make a double bond. And I think I gave, did I give oxygen? I think I gave oxygen 5. 1, 2, 3, 4, 5. It's 6. It's 6. Give it another dot. Okay, so now I have a double bond between each of the carbons and an oxygen, so I'm just going to redraw that. Double bond oxygen, and then put my lone pairs kind of as far apart from one another as they can get. Okay, so now I have this complete structure. Carbon has, let me see if I can erase this. Carbon has 2, 4, 6, 8 electrons, and then each oxygen has 2, 4, 6, 8 electrons. So this structure looks good. If you wanted to know right off the bat that it would need double bonds, you can do that. You can go, there are 3 atoms, and each of the atoms needs 8 electrons, right? There's no hydrogen, so they all need 8. That's 24. Then available, carbon's got 4, oxygen has 6, times 2 gives you 16. So that gives you 24 minus 16 is 8, divided by 2 gives you 4 bonds. So you would see that you had your carbon and 2 oxygens and you needed 4 bonds. Then you would say, okay, my available were 16, my shared are 8, that gives me 8 electrons, divided by 2 gives me 4 lone pairs. And so I would just add them to my outer elements to complete their octets. Okay, so based on the Lewis structures you drew, establish a pattern of rules. Really write your rules before you look at mine, but I wrote 2 sets of rules. I wrote one rule on the logical way of using the Lewis structures in order to draw your diagrams, or I did the needed, available, shared method. And that's these down here. So either way is fine. Then you need to practice. You just need to practice. So you can screenshot, you can look at these so that you can check your answers, but you just need to do practice. Just keep practicing. The more you practice, the better you're going to be at it. Okay, that is the end of Lewis structure.